Right, so we just did our first Darcy's Law calculation, and we drew it in two dimensions. It looked like this. So we had a vertical slice of the earth, and we only had two wells, and the water we knew was flowing either from well B to well A or from well A to well B. But in reality, the world's a little bit more complicated than that, right? So imagine that you're working for an environmental consulting company, and a farmer calls you up and says, "Oh, I just had this spill of of pesticides, concentrated pesticides out on my field, and I don't know, who knows? It sat there for a while, it soaked into the ground, and I need you to come figure out where it's gone so that we can clean it up." So you get called out to a field. Here's the field. This is north. There's a scale on the map, of course. Let's say that's 100 meters. And the spill site was here at the X. And you want to know where's the water going and how fast is it going, and because pesticides are water soluble, and so wherever the groundwater is moving and the rate at which it's moving, that's probably how fast in the direction that the pesticide has moved. So how would you tackle this problem? How do you know where the water's going and how fast it's going? Well, what you want to do is think about the fact that when you drill a well into the ground, you're eventually going to come to a point where water flows into the hole. And that point is the water table. And if you imagine drilling lots and lots and lots of wells, you would see that the water table is sort of an undulating planar surface. It's not just a discrete point, but like if you could scrape away all of the dirt and rock until you got down to the water table, it would look like a pool, right? It would just be a layer of water just sitting there right at the surface. So we need to know what the orientation of that water table is, because the orientation of the water table is basically telling us what direction the water is moving. So in order to, if it's a plane, if the water table is a planar structure, then we want to define a plane with three discrete nonlinear points. So we're going to drill three wells A, B, and C. And we pull out our topographic map and we look at the elevations there. And let's say that the elevation here is 980 meters. And here it's 960 meters. And here at C, it's 965 meters. Okay, that's for these individual points where we're going to drill our well. And we drill the well, and we find that we have to go down in order to reach the water table. Depth to the water table is 50 meters here. Depth to water table is 40 meters here. And depth to the water table is 55 meters here. So what is the elevation of the water table at point A? Well, if you start at the land surface at an elevation of 980 meters, and you drill down, not going to drill right below a tree, but that's the point, drill down 50 meters, that's where the water table is. So what's the elevation of the water table? Well, it would be 980 minus 50 would be 930 meters. So the water table is at 930 meters here. The water table is at 920 meters at well B. And the water table is at 910 meters here. Okay? All right. So the way to figure out the orientation of a plane from three discrete points is often referred to as a three-point problem, because you need 3 points to define a plane. And the way you do it is pretty straightforward. What you need to do is you need to define a contour line. So step one is define a contour line for the water table. Remember, the water table is just that imaginary, that surface that exists where water rises up to in the bottom of a well. And if you connect all those dots, you get this sort of planar surface running across the ground. Okay, so you need to define a contour line for the water table. So a contour line is a line that's connecting points of equal value. And because we're defining the water table, we're going to be defining the elevation of the water table. So we need 2 points that are both the same elevation and that are on the water table. So if we look at this, we have a water table at 930 meters at well A, 920 meters at well B, and 910 meters at well C. So none of those are at the same elevation. So what do we do? Well, we can determine where, let's see if I can draw this line. I'll use something as a straight edge. We can determine where the second point is going to be, because we know that if you pick the highest value, 930, and the lowest value, 910, we know, just like we did in our contouring exercises, that somewhere between 930 and 910 has to exist 920, right? If you go from 910 to 930, you have to go through 920. So I'll draw a little line here, try to. That's between point A and point C. And remember, this is 930, this is 910. So where is 920 along this line? Well, halfway between 910 and 930 is 920. So half the distance between point C and point A would be 930. So right about there would be 920. That distance is supposed to be the same as that distance. It's close. Okay, so now what we can do is we can draw a contour line because we have 2 points of equal elevation. That's at 920, well B, and that point we've just defined is at 920 feet above, or meters above sea level. So I'm going to draw a line in pink here. So that is a contour line of 920 meters. Now, if we're going to define the hydraulic gradient and determine what direction things are moving, we need to have 2 contour lines. You can't just have one. So what do we know about contour lines on a plane? Here's a planar piece of paper. And if you can see that, the contour lines would have to be, if I drew contour lines on this piece of paper, they would look like this. So they are parallel to each other. So if we know the orientation of one contour line, we know the orientation of all contour lines. So I'll pick another one of these spots, 910. This is well C, which we know has an elevation of 910. And I'm going to draw a line through C that's parallel to this pink line I drew up here. This is another contour line, because contour lines on a plane are parallel to each other. And the question is, what is the elevation of this contour line that goes through point C? Well, it's a contour line of the elevation of the water table. We know that the water table is 910 meters above sea level here, so this contour line is 910 meters. So now we know what direction the groundwater is moving. The groundwater moves perpendicular. I don't know if this is going to show up. That's probably not going to show up. The groundwater is going to move perpendicular to these contour lines. So it's going to move like this. Hope that shows up. And it's going to be moving from high hydraulic head, or higher elevation of the water table, to lower hydraulic head, lower elevation of the water table. So it's going to be moving in this direction from 920 meters to 910. And it's moving perpendicular. This is really important. It's moving perpendicular to the contour lines. It's moving from here to here, or from here to here. Okay? So that's the idea. So what do we do now? Well, we write Darcy's law again. Darcy's law is Q is negative K dH dx. Q is negative K. What is the material that we're moving through? let's say it's a sandy loam, let's say, which is kind of a sand silt mixture. It's pretty good for farming. And let's say it has a hydraulic conductivity of 10 to the minus 4 centimeters per second. So that would be 10 to the minus 4 centimeters per second. And what is the hydraulic gradient? Well, it's a change in hydraulic head over a distance. So what is the change in hydraulic head from along this line, from here to here? Well, it's 920 minus 910. And what is the horizontal distance? Let's make it easier on ourselves. Let's say that that's 100 meters. Let's say that's also 100 meters. It's not, but let's just say it is. So let's say that's 100 meters. So what you end up with is negative 10, when it would be a negative 100 meters, because this would be 0 and this would be 100. So you'd get when you subtract this from this, you get negative 100. But anyway. Okay, so we get 10 to the negative 4 centimeters per second times 10 over negative 100, which is negative 10 to the negative 4 centimeters per second times negative 0.01. No, 0.1. Negative 0.1. And so that would be positive 10 to the negative 5th centimeters per second. All right, so what have we done here? Through all this, we've basically said, okay, if the spill was right here, we know that the water is moving in this direction. It's moving in that direction, and it's moving at 10 to the negative 5 centimeters per second. So in order to go horizontally, in order to go 1 centimeter would take 10,000 seconds. So the odds are that this farmer doesn't have to worry that the spill has gone very far, because the hydraulic conductivity, the flow rate, I should say, the flow rate of water underneath his field is pretty slow. So presumably then the plume, the area that has been contaminated, is in a pretty small area, and it won't be that hard to clean up.